is what is the first and probably the major talk of the day. And let's go and talk about this. Okay, now we have, I want you to go and keep in mind what is the model so that you know when the particular assumptions can be violated. The model that is going to be around the volumetric estimation, okay, is going to be the shale on top of a shale sand mixture with or without a fluid. Then underneath it, there ends up being a shale that's the same as the top shale. And remember that when we go in risk amplitudes, we actually had an even simpler model that didn't have this shale underneath it. And so, you know, when can this be violated? Well, what do you think of something could be that could violate this assumption? And it's kind of a common thing in terms of violating it. Any suggestions? Okay. Okay. Well, when there's a gradational bottom, okay? If it sort of changes slowly and you can't see the bottom, that can cause a problem. Right. Okay.
Sand with another fluid.
What's that?
Sand with a different fluid.
Sand is a different fluid than what you considered. Okay, that's another thing. Okay. What about this? Okay. The top shale does not equal the bottom shale. Okay. There's another way that this can be violated. Okay. And
what if the shale at the bottom is actually multiple layers, and you thought that it was one layer?
okay, that we actually have another sand layer down here that actually goes and interferes with this. Okay, so the model can be more complex. Okay. Okay, and we'll talk about, there are ways that we can handle these cases, and we'll talk about that in lecture 12. Okay, but always be aware of what your assumptions are here. Okay, and how do we go and sort of go and extract amplitudes? Our preferred method, if we can do it, and you'll see why in a second, is to go and do what's called a sparse spike inversion, or I like to call it a sparse spike aggressive final deconvolution of the data. And this ends up helping and you'll see, helps remove or address some of the issues around tuning, for instance. But you do need to have a well on your survey in order to be able to calibrate and do this. And so we will talk about what do you do when you can't do this. And you sort of drop back in that case and use the real sort of cheap man's sparse spike inversion, which is called run sum. Okay. And what's the type amplitude extraction that we tend to do on a sparse spike inversion? Well, this is, and what we tend to work with is the sort of the band limited version of the inversion. We also don't go and change those into impedance units. We actually work with it before it's converted, and we work with it in terms of reflectivity units, okay? So that the sparse spike inversion that you get has already had this millivolt to reflectivity calibration, so that if you go and extract an amplitude from here, it's already effectively had that calibration that Dave talked about done to it, okay? And again, it's evidenced by, these are units and they're reflectivity units in this. Now what we do is we identify the hard, in this case, since we expect the sand to be soft, and we know that because of our modeling that was done before, that we go and we pick the sort of the hard streak on top of it and the hard streak underneath it. And then the particular program will go and find what the biggest negative is in between these two hard streaks. And for interpreters, I think that this actually makes your job a bit easier, because these hard streaks normally are associated with shales or sequence boundaries or close to sequence boundaries, and tend to be more laterally continuous and easier to pick than the more nervous sand deposition in between these sequence boundaries, okay? You can, if you've gone and picked the peak, we can search for these things on the side, but that ends up being a little bit more problematic and also a little bit harder to pick. And so that's what I sort of promised at the beginning, where I said that actually picking your sequence boundaries is actually the best way to sort of lay the foundation for your amplitude extraction. And you don't have to go and get all twisted off on being able to follow each of these sand units, which tend to go much more quickly than the hard units on either side. And now if you take a look at the wiggle, and this actually I flipped it so that it ends up being a hard in the middle and a soft on the two edges. But we've gone and shown that we have three events. We picked these two hard streaks, which are called P1 and P2. By the way, our software calls them P1 and P2 too. Then there's a pick in the middle, which is that major trough, which ends up being called P3. And there are a couple of things that we define. The first thing is we draw a particular secant line, okay, that just sort of touches P1 and P2. And then we define the secant amplitude as a distance, perpendicular distance from this line to the peak. And the secant area as the area inside here, okay, above the secant line and below this. And Dave will talk a bit later on why we go and do the secant, and it has to do with phase sensitivity. That if you roll this phase-wise, that this sort of goes up and down into leading orders and sensitive to sort of modest-sized phase differences. And even if you're off by 45 degrees, you find that you don't have a significant change in what the area is, or the amplitude, okay? And we also then define the width in terms of the width half max with respect to the secant, okay? And let me go and talk a little bit about a little subtlety about these edge peaks and sort of a practicality. And that one thing that tends to worry people at the beginning when they look at this, if you think about it, isn't really that big a deal, is that the way that this stuff tends to look practically is like this, okay? That you get a big peak and you get little wiggles along the edge, okay? This peak normally is a fairly definitive thing in terms of looking at it, but many times you're going to ask yourself, and just depending upon even noise levels, that whether or not you pick this or this in these two cases, it's going to be a question mark, okay? But now let's go and ask ourselves, you know, sort of what happens if we go and look at the, you know, the change of whether or not we pick here versus here, okay? Well, in terms of this width, okay, it makes a big difference. But in terms of this width, it's not going to really make any difference, okay? Also, if you take a look at it, in terms of the secant amplitude, it doesn't make much difference on whether you pick here or here. And also in terms of the area, whether or not you include this little blip here doesn't make a large amount of difference, okay? So if you go and see that you sort of are jumping between sort of one of these sort of small little blips to the other, okay? The one thing to keep in mind is that the effect of this on the things that we really care about, which are this width W, the amplitude A, and the area, really has a very second order effect on it, okay? And again, just sort of keep that in mind. Now, the other thing that's really good to know is that, okay, sort of what is the amount or the net sand that we actually have in this particular interval? Because we want to go and estimate what the volume is. And that ends up being the net sand, okay? And what's really nice is that if you take this area and if you multiply it by what you think the velocity is of that sand, which you tend to know fairly well, probably within 10%, and you divide by 2 times the expected reflection coefficient of that sand that comes from the modeling, okay? Then what you get over here on the left-hand side is the amount of is the feet of sand or the meters of sand, depending upon the units that you have in the velocity. The 2 comes about because we're dealing with two-way travel time. Okay? But the other thing to note about this, there is no calibration factor on this. The reason why there is no calibration factor on it is because we are dealing in this case with a seismic inversion that has been calibrated to the well log. Okay? I will talk a bit later about another way of doing this when you end up don't have a well log and need to calibrate to the data, and there will be one calibration factor that you'll need to go and figure. But also I'll go and as you go through the exercises, if you're working an area with multiple levels or different sands, okay, don't figure out your calibration, the different calibration factor for each sand. You figure out one calibration factor for that field and you use it for all your volumetrics. But know there may be a systematic high-low variation associated with it, but that will just be what the uncertainty is in the calibration factor.
Yeah. If it's laminated sand, it's causing that, is that going to give you an accurate sand?
That is correct. It'll give you an accurate estimate because we have calibrated the reflectivity. And if it's laminated, it's going to have half the reflectivity and therefore will have half the volume. Okay? Now, you'll see in the other formula we have an explicit net to gross, and that's going to be the net to gross over which you've decided to normalize the data. So if you have made a mistake there and circled an area and said, I think that the net to gross over the seismic loop is 80% and it's really 50%, you will make a mistake, and it will be dependent upon what the net to gross is at the position where you normalized it. But in this case, it ends up being taken care of by the seismic well time, okay, itself. It's ended up figuring out what that factor should be, and it gets taken into account. And again, this is, I haven't seen this out in the industry, and I'm really was surprised, and it's evidenced by the fact that everyone always tries to convert their seismic impedances, their seismic inversions into absolute impedance values. In fact, it takes a lot of work because you have to have these low frequency models, and it actually, you lose information when you do that, and you're much better off keeping things in terms of the relative reflection coefficients, which are the natural units that come out of the sparse spike inversions. Okay, we ended up going through some benchmarks, and we ended up trying to have a fairly little devious model, and you'll see that even though it's simple, many of the it ends up showing up issues with many of the different inversion codes, and some of them you scratch your head because they probably didn't even try these basic benchmarks in their code development, which I think are pretty obvious ones. What we have is a wedge of soft sand. We have like a little shale plug channel-like feature in the middle of it, and we've arranged it so tuning thickness is this thickness, okay? And we did that because it's kind of diabolical. It's sort of the worst case scenario if you're actually doing one of these inversions. And if you take a look at it, what we do is we look at the amount of sand as a function of position as we go from left to right. And we went in, and the right answer is a straight line with this little divot taken out of it due to the channel here. And it turns out that if you go and do the seismic inversion and follow this prescription that I talked about, that here are the results with several different methods. First, if you sort of do the cheap man's inversion, which is the run sum, you end up getting the black line here, which obviously has a significant deviation from different tuning effects for the thinner sands, and has about a 40% underestimate for the particular thicker sands. If you go in, though, and start doing the sparse spike inversions, well, first of all, the reds, by the way, are Hampson-Russell. And I'll probably show an example. They have all types of trouble in terms of getting stuck in local minima. And this is the particular reason why we don't use Hampson-Russell within DHP in terms of its sparse spike inversion. Jason Geophysical is industry inversion number 2, which is the blue line. You see it has some problems right here as you approach tuning. It has a bit of bias when you end up coming up to the thicker. And in fact, if you add on a low frequency model, which many people do, and I'll show you that it actually gets worse. It doesn't get better. So that doesn't, for those of you who are aware of that technology. And we end up having an in-house inversion that was developed by Stefan Malot's group at L'École Polytechnique, which ends up giving you the particular black dots that overlie the answers. And for you guys from mining, is that we can use this to our heart's content. And that if you go and take a look, industry inversion number 2, to get 1 seat of that is about $200,000 in terms of that software. So again, I sort of wanted to let you guys know that we have good tools to get this and at sort of efficient cost profiles going.
Like we have a proprietary inversion software is what you're saying, which
Yeah.
is black dots? And that's fairly new though, isn't it?
I mean, we probably have had it in hand for about 3 years. We also, there are some even more other interesting twists to this inversion. And it's a multiple stack inversion. This is simultaneous inversion. And also we can flip a switch and use a flavor of it that imposes a certain amount of lateral continuity that improves performance. And I'll talk about that in lecture 12.
Because I think one of the projects that I've done an inversion on, we didn't use that, we used the JSON product.
That's right. And I mean, it's not a bad, and especially for exploration sense, that we consider that it has acceptable performance.
Yeah, because what I notice is it underestimates net sand thickness, which I'd rather underestimate it than overestimate it.
That's right.
From the sense of if it can jump an underestimated hurdle economically, then that's a good thing.
Yeah, that's right, yeah. So, I mean, and you sort of know where it can happen and sort of about the size of it. And so we consider it, acceptable performance, but this also means we aren't running out to buy more seats adjacent. We had the seat, and that came from the early days of when I was here, and we continue to use it. Bruce is very skilled at utilizing it as a good user interface, and so we have continued to utilize that. But I mean, fairly early on, we saw how bad Hampson-Russell was, and put the X on it. And we know what's wrong with it, but I mean, I can't get access to the source, and we got something that works. 2 things that work well.
So how many inversions can you actually carry out at a time on their own, using their own inversion software?
In terms of,
Say, I want to do inversion.
I mean, well, we can run as many copies of it as we want. We can distribute it out on a cluster. You've distributed it on a cluster, haven't you? So we put it on as many processors as we can find.
How many LANs do we have?
What?
He's asking how many LANs do we have to actually run it.
Say if we want to do 3 inversions at one time. Can you do that?
Yeah, well, I mean, I don't know. How long
You
would
can
you
try and
say?
get to do it, Jack. You really need to.
No, I'd rather do it.
Yeah, no,
How
I
many
mean,
logs you got?
I think if you got a week, I mean, I can't see. I mean, the biggest time constraint is deriving the wavelets. I think that it ends up being the amount of, and also doing the tests of what the parameters are. you press it, maybe it'll take a day or two or something max to flip the turnaround, and it'll probably take a week, playing around trying to understand your wavelength. So, yeah, as many as you can throw at us, we can end up doing. I think practically we're more limited by how many long gangs we have.
Yeah, that's
Yeah, Jack, I think I can answer your question. The only person we've got in the QI group now who can run this software is Long, and I think in terms of turnaround, to do a elastic impedance inversion, I think we're looking at about a month's time for one person.
And also, a lot of that is involved, and correct me if I'm wrong, Guy, with careful care and wavelet derivation.
That's right, Chip.
And also setting parameters and interpreting and quality controlling the results. We're not limited by how many lungs we can have, for instance.
What do you mean? We're not limited?
I mean by how much compute power, how many
no.
CPUs we can get
That's right,
access
yeah.
to. So. And I think along that lines, though, too, is that there's a particular target, especially for the mining companies, of building up the expertise within the RBO group and getting a couple more people that are skilled at running that and having that capacity there. So, anyways, that's the okay. And I also want to talk a bit here about what is inversion and what inversion is not. Okay, I think commonly people will go and say that inversion enhances high frequencies and boosts high frequencies. Okay. And I really think that that's an incorrect way of looking at it. In fact, I think there's a whole bunch of snake oil salesmen or medical charlatans out there coming up with their ways of boosting high frequencies. Well, there's a very easy way to boost high frequencies, and that's to go and apply a filter that boosts high frequencies, right? Well, then I think some people will say, well, it improves and increases seismic bandwidth. Well, that's probably getting a little bit closer because it's not only about high frequencies, this is about low and high frequencies, but I can design a filter that can boost low and high frequencies, okay? Is that the right thing to do? I think we saw a couple chuckles here. Now, I try to talk about a good inversion is about spectral restoration, okay? And we're trying to restore the spectrum to what the well is. And if you go and take a look at the well reflectivity as a function of frequency, it goes and looks like this, okay? It's the green line. Now, if we take a look at the seismic data, okay, that we end up seeing in this case that it ends up being the red line. And boy, look, it has more low frequencies than the well. Great. Well, why would we do anything? Because if we go about doing the spur spike inversion, we get the blue, which reduces the low frequencies, right? But I think most of you know that the blue line follows the green line, which is what the well looks like, out here to about 80 hertz, at which point the well reflectivity continues to go up. I think you'll recognize that this is actually the limit of where we weren't able to restore things because the signal has gone down into the noise. In fact, 80 hertz is pretty remarkably high, okay, to begin with. But what has happened? Well, the seismic data has had put on a wavelet which has more low frequencies than high frequencies in it, and thereby has gone and has colored the data with the wavelet spectrum. And so inversion is all about taking out the color of the seismic wavelet and restoring things to what the well looks like, okay? And after you do this, it may look like it is a lower frequency signal. Well, it looks like it's a more low frequency signal because the geology probably is lower frequency. And so there have been times when you look at it, a good inversion just doesn't have more high frequencies. It actually has a closer comparison to what the well itself looks like. Okay? Also, the thing to take a look at is that as you go and do some seismic inversions, the particular profile of the amplitude itself can change. This was over in particular with respect to scaffold, but after you went and go and had a careful seismic inversion, you ended up seeing more changes and better sort of patterns in the amplitudes. And it really came about in this case because there were multiple sands sort of interfering and sort of going and sort of complicating the picture. And then once we go and get these extracted secant amplitudes, that if we go and compare these secant amplitudes in terms of reflectivity to what the model reflectivity are for each of these cases, and this is the results of your last exercise, that we'll talk about what the formula looks like to be able to take these calibrated reflectivity numbers that have come out of this secant amplitude extraction and to be able to transform those into probability of a particular, in this case, of oil, okay? And that has to do with that risk, that little spike at the beginning, okay? Then you also can go, and since we have that formula associated with how many meters of net sand in terms of the area map can be gone and transformed into a net sand map, and then this net sand map can be integrated to get a resource estimate, or what's called in the petroleum area or reserve estimate associated with it. And that's the most likely. It's not the particular uncertainty in it. In fact, you have to go to what we call our phase 2 analysis to actually get a good estimate of what the error bar is. And I want to go and just point out one thing really quickly here. It has to do about assumptions, okay? And what we found is that from here, these numbers were a bit too high, okay? And let me go and ask a question, okay? What particular assumption do you think was violated in order to that caused this, okay? And where we had the problem was right here. Okay, what assumption do you think was violated around this area that caused the problem? Any guesses?
Top shell versus base shell.
Top shale versus base shale, okay? And when we went in and did and allowed a more complicated model, we saw that that particular bias was removed. And for those of you who didn't notice, it's coming about because of these blue streaks that come and go on either side. And that you can see in certain cases that what's above and below is not the same because of changes to the bounding lithologies. It's actually kind of interesting too, is another thing that we found, and this can actually, in terms of the particular inversion, came about from sort of looking in more detail at the particular signal to noise ratio, and also the particular way that people try to remove the low frequency after you do the integration of the reflectivity. Here is the model that we were talking about before. Here is sort of a raw, sort of result that comes out of a sparse spike inversion. After you go and sort of use a standard sort of low-cut filter, that you find that you end up matching the well better, the signal-to-noise level increases. But the interesting thing we found is that when we sort of stumbled upon this fairly simple way of removing the low frequencies, not with a low cut, but with sort of a moving average, triangular average, that we ended up getting better matches to the well log or the particular underlying model. But it ended up showing up, if you take a look at something like Scarborough, where you go and use a standard low cut on it versus the particular methodologies that we ended up employing, you end up seeing, let's say this area here, you see there's a lot more low frequency information that comes through that is correlated to what you end up seeing in the well. You know, for instance, here you see this large amount of red. You also go and see, you don't see, you know, this particular quick change to a hard underneath the fluid contact that sort of restores back to the zero mean. You see sort of less of this sort of overshoot and sort of coming back to a mean. You see that in general, the whole area underneath the objective is harder than the particular objective section here.
If the instruments that you put down these holes, these that give you your well log, are only sampling a small area, can you trust their low frequency information as much as you trust the high frequency information?
Well, in this case, we actually do have information, more information about, it's over a fairly large area compared to this here. And we do know that this is all fairly uniform and is also quite a bit softer than the area right on top of it. So we do have some reliable information in that case. And so another particular message is that you can in certain cases get better low frequencies if you take some care about how you band limit the data versus what happens in general in the industry. And also I just want to show you quickly that people will spend a month or two trying to go and get some of these low frequency models to sort of put on to some of the JSON inversions. And what we end up finding is that if you go and put on sort of a standard low frequency model, that if anything, things get worse, don't think that it ends up sort of reducing the particular bias that you end up getting. In fact, it sort of is preordained in terms of the bias that you sort of, whatever model you put on is kind of what you end up getting out. And I can sort of talk to some people on the side about why there is a sort of fundamental problem in this. We also have things that take into account and a switch can be thrown in the inversion to enforce lateral continuity where there should be lateral continuity and allow discontinuities where there should be discontinuities. And this takes out an effect people sort of call this curtaining or this vertical striping. And you can see the effect of one of them here that has really been significantly reduced, but you do still see there can be significant discontinuities preserved in the data with the reduction of the curtaining. And this actually ended up being the $80 million solution, by the way. Does anyone have an idea of where this ends up having its largest value? It's in taking standard definition TV and taking it into high definition, interpolating it into high definition TV. Because this actually will go and allow you to identify the fact that one frame is similar to the next and use that information in order to be able to go and increase the XY resolution of the picture. And this particular technology is about ready to be put by the Zoran Corporation into probably all of our HD TVs and DVD players, by the way. And that ended up being the $80 million application of this stuff, not the stuff in the seismic. So I sort of call this a strange things happen on the way to the forum type of research activity. So, yeah.
That we found when we do the cross-line direction, it doesn't look as
It doesn't?
Yeah.
Okay.
Yeah, I think, at the moment what we find is that with 3D data, I suppose any operator that works in 2D looks great in the line, in the direction that's being applied, but then when you look at the cross line, so really I think that 3D it needs
3D
some
needs to be
into 3D. Good point. Okay. We also have a version of this that adds in the constraints that if you have two stacks, if they have reflectors, that the reflectors have to be at the same location. Here are sort of the sparse spikes. You can see, for instance, this one ends up flipping polarity a bit going from near to far. This one definitely flips. This one does not flip going near to far. And it sort of allows you to understand the ADO better, but also acts as a constraint on a modestly under-constrained problem that also sort of helps you get better results. But one thing I really do want to sort of accentuate to people, and that we're tending to do now in a modestly routine way, is taking a look at spectral signal-to-noise ratio comparisons, okay? Because a lot of times people will go and say, hey, I have a process that's better, or I've improved the processing. Mark will come up and say, I think I'm doing a lot better job, okay? And what we've ended up in doing is taking a look at, as a function of frequency, how well the data matches the well log, okay? Because if you go and say I've increased the signal-to-noise ratio, have you done that for the high frequency, low frequency, or all frequencies, okay? And what you should see is that if you have improvement, at least for some frequencies, you should be able to increase the signal-to-noise ratio due to the process that you're applying. And in fact, you can go and easily see now that the bandwidth, because we have a signal-to-noise ratio as a function of frequency, ends up going for this reprocessed data that Mark, ended up working, quite hard on, goes from this point to this point, which are the zero crossings, where before, I don't know, this bump, it probably goes from here to here. And so you see that you not only improve things at the high frequencies, there's a very significant improvement of this data at the low frequencies on how well it was matching. And this ends up coming out sort of naturally from a wavelet derivation process that we end up having, an analysis of the results that end up coming out of that, okay? And it's kind of interesting that when, again, I go and I see people in industry and they start saying, hey, I have this great inversion process, I say, what does the spectral signal-to-noise ratio look like? And they normally, or even just the signal-to-noise ratio, look like as compared to well logs, and they sort of scratch their heads. But I encourage this type of thinking, which is a quantitative way of really answering the question of, have I improved the data in a way that we really care about? In other words, have we spectrally restored it? Have we restored the data to look as closely as we can to what the seismic data looks like? Okay. Now let me sort of talk another little bit in terms of amplitude normalization. And that there are a couple of different types of normalization that people go and talk about. And this is really, there are two things that can come into this. One are sort of processing non-idealities or particular things above your objective that can shadow it, like salt or anhydride stringers, or just other shallow gas bright reflectors. And there are other things which happen to do with the fact that, hey, we don't have a well, and now we're going to be kind of desperate to try to normalize the amplitudes into reflectivity units. If we start with an amplitude A, and we have one of these problems that we have some like acquisition striping, and if we're lucky enough to have a reference reflector which we think should be constant and is not, we can extract that amplitude map and divide by that amplitude map in order to be able to take out the effect of that striping or that shallow gas reflector or that let's say shallow anhydrite or salt that we end up having. But the one thing to note is the difficulty with this is getting a good reflector that's really constant and doesn't have geology itself on it. And that tends to be the particular, sort of challenge with respect to getting one of these background maps. And we'll go and sort of see that in terms of the first example where I've actually sort of put on sort of some synthesized striping. Now, if we go and then normalize to, then we have still the problem of how do we normalize to sort of go from millivolts into the reflectivity units. And many times we'll go and find a down dip brine sand or go and find what we think is a shale and then go and divide by that and reference it to that sort of reference reflector. Okay, or it could be a known hydrocarbon sand somewhere in the section. And that's normally sort of what's called the up-dip A over B type normalization of the data. And so I wanted to go and sort of distinguish between one of these map-based and some of these normalizations that we resort to when we don't have a well log in order to calibrate the data. Okay. Probably go over and flip over to Dave and for a little bit now.
Yeah, just a few minutes. Mike's already sort of told you the answer. That is that you use secant amplitudes normally in your QI methodology, and with good reason. I want to just give you a little background on why you might do that. There's a lot of ways you can measure the amplitude of a seismic event. What are some of the characteristics that you might seek so that you would feel comfortable with the amplitude you've measured and the comparisons of different amplitudes? That's the question of the day. And I got down here on the bottom. There are two of them that you certainly might think would be useful. Would be extensive. You'd rather have an intensive rather than an extensive measurement. What do I mean? With physical properties, extensive measurements are properties that depend upon the quantity of the material you're measuring. So the mass of an object, or the amount of heat required to raise that mass to a certain temperature, or something of that nature would be an extensive property. An intensive property is something which doesn't depend on the quantity of the sample that you're using to measure. And so think of that this way. And the second thing would be you'd like something that isn't terribly sensitive to the phase of the seismic data you wound up with. All right, we're all trying to process the zero-phase seismic data, but we don't always succeed. And sometimes there's a little bit of phase left in the data. And it's a complicated thing to say, well, my data is zero phase everywhere. No one can prove that, really. You only have a few wells where you can compare it, and it's difficult to do, or can be difficult to do. So you'd like to have something that isn't terribly phase sensitive, so that your amplitudes are not varying for reasons that you can't interpret. So let's think about a couple of ways you could measure amplitudes. One would be RMS amplitude. Just take a gate. Mike said, well, I'm going to pick the top and the bottom, the P1 and the P2, and I just want an RMS between P1 and P2. Or somebody else might say, well, I may not pick P1 and P2 exactly correctly. He showed you a case where you could, there would be, or that case right over there, you might choose this one, or somebody else might come along and say, I really ought to choose that, or what have you. So there could be variations in the gate width. It's fairly obvious that RMS amplitude is an extensive kind of thing. If you take a bigger gate, you'll get a different answer, and if you take the smaller gate, in this case. Second thing is, well, that's enough sort of to kill it. It is a little bit, it's weakly phase sensitive. If you roll the phase, this would be a zero phase. If you roll the phase of this, you'll find out, it's a simple way to do it. We got one of these things in place. Simple way to think about this would be, if you have, I'm a very bad drawer, but let's imagine that we have this thing. Talking about it. Alternatively, the phase roll of that, which would be 90, would be something that looks more like this. Okay. And, well, here we've got, say, 2/3 above the line. Let's do it this way. 1/3 each below the line, because we have 0 dP, 0 DC. And if you square those, you don't get the same answer as 1/2 above and 1/2 below, which is what the 90-degree phase would be like. So the RMS of this is different than the RMS of that, but mildly different, okay, 10% or something. So that's not very good. RMS is not really what you go for. A different thing you could do would be say, and this would be the easiest thing in the world to do, say, well, hey, I've got the DC removed. The amplitude is, find that peak between those two extremes, Bingo, the zero to peak gives me the amplitude. How about that? Well, that's an intensive measurement. It's not data, it's not dependent on anything you chose about the event to get the value. Everybody will get the same answer. It is, however, phase sensitive, and that, again, it's not hard to see suffice.
Weighted some of the first few.
The secant, we might call the secant amplitude, is intensive as well. It doesn't depend on something that you chose about the data.
That also gives you
It's data dependent only. So everybody will get the same answer, and it is, as Mike pointed out earlier, fairly phase insensitive. That is, there's very mild phase sensitivity if you play around with it, but it's not bad at all. But for the models, the simple models that we're discussing here, you can always contrive a model which will give it trouble. But how long, that is, Mike talks about having another sand layer below or shale below that's quite different than the shale above. This is still going to be superior to zero phase. Zero peak amplitude measurement in terms of phase sensitivity. So that's why he's using secant amplitudes, at least some motivations for why he uses that. So, I think
I did want to go and sort of caution you about when you're extracting amplitudes of this nature, is that a way that you can go and possibly underestimate the amount of sand that you have. And that, many times if we go and have a profile such as this, we would go and say, this is sand 1, this is sand 2, I'm going to go pick this, this, and this as my particular 3 points, okay? And I want to know how much sand is in each one. Well, one thing to be careful of is that the secant area of this plus this, which is going to be this area plus this area, does not equal the secant area of the whole complex, okay? So whenever you have two sands that are interfering with each other, note that if you try to separate them, okay, that you're going to go and underestimate the sand, okay? So I don't go and discourage you. If you do want to separate them, but also calculate the sum and go and make sure that you scale up these individual maps to give you the right sum and sort of figure out the scalar difference between the two and sort of go and sort of manipulate it back up if you really need to go and separate out those particular sands, okay? And that's probably why you end up seeing that I'll a lot of times go and extract for the package rather than extract for the individuals. But you can go and extract for the individuals if you would like. There are other ways that if you're using what's called composite amplitude thickness, if you split this up, that you don't have the same effect, but there are also other reasons why with that as a method, there are other reasons why that it's probably not recommended that that be your first resort in terms of addressing this problem. So just a little caveat to sort of remember when you're going and doing this.
Like the formula you had up before, quite a few slides back, will that still apply in that case?
In terms of when you split them up?
Oh, no, when you don't split it up.
No, that's the one where you don't split it up, that applies and is theoretically correct. When you don't split them up, you will get the right sum of the two. Let me go through and I want to sort of talk about different methods of amplitude extraction you may see and different methods of inversion and sort of show you the benchmarks that we've done. And I'm going to give you a flavor for when we make the particular recommendations and we say, extract secant, amplitudes and areas off of run sum, and we like Hampson-Russell, we don't like Hampson-Russell, we do like Jason, and we like our internal inversion even better, and we prefer to extract off of spur spike inversions rather than off of off of just simple run sum. It's really because we've taken very careful look at benchmarks, okay? And one major thing, and I know Rick, you talked about it, is tuning, okay? Because tuning can boost things, okay? Can boost them up to a factor of 2. If you remember, the amplitude anomalies we're looking for many times are factors of 2, and so that's a false positive. And what do we do to try to recognize that and try to reduce it and mitigate that particular problem, okay? And you'll sort of see what I mean by tuning in a second. But if you go and take a look at, here are the synthetic seismic of that benchmark model I showed before, and you can see how diabolical we've been with that little plug and how we're right on the tuning peak right when we get there. And you can tell that because the spacing here is sort of exactly sort of the width of the trough to peak of the wavelet, which maximizes the tuning effect. And let me go and talk about a couple different, two major definitions of the way to do amplitude extraction. One method that's utilized, and it tends to be pushed and is very ubiquitous, say, throughout the ExxonMobil empire, is composite amplitude thickness. It's done on reflection coefficient data. The beginning or the top of the reservoir is the particular negative kick in this case. The base is the positive kick in this particular phase. Composite amplitude is the average of the absolute values, and the composite amplitude thickness is this composite amplitude multiplied by the difference between those two. You end up finding this is insensitive to phase. It has good properties. Okay, so I have to say this is a solid thing to consider and to utilize. And you find that this composite amplitude thickness, in the case that you don't have it calibrated, okay, what do? Well, this is a modified formula in the case that you don't have things calibrated by a well log, okay? And what goes in here is the interval velocity of the sand again. But what you end up having is 2 times the amplitude in millivolts where this you can find a thick sand, okay? Greater than tuning thickness, okay? And I'll talk about that a little bit more in a second. And you also multiply it by what you think the net to gross is in the area where you picked this A naught, okay? And it's the net to gross over a seismic loop, which is about this 30-meter thickness, okay? It depends on your bandwidth. For this 80 to 100 hertz stuff, you know, you're getting down to the 10-meter thickness in terms of tuning thickness. But this is where you can't have a problem if this net to gross was different than what you thought it was where you were normalized, okay? And also, if this is actually at tuning or below tuning, this can also be a problem of where the assumption ends up being violated. So again, A naught needs to be where you're greater than tuning thickness, and the net to gross here is the net to gross over the interval where you picked A naught and over a thickness which is the particular thickness over which you, or is over the width of the seismic wavelength. Okay, but what does tuning look like? Okay, what happens is that there is a constructive interference right when the thickness of the layer ends up being sort of the trough to peak distance of the wavelength. Okay, you get a constructive interference, and this will vary depending upon exactly what type data you're talking about. And this A naught is where you sort of get over the tuning thickness and you think you're dealing with a thick sand, okay? And you have to go and find this area, and it can be difficult to do, okay? And we'll get into some of the practical conundrums and the exercises. We have actually 3 exercises, since this is so important, at the end of this section, really talking about how do we go and do amplitude extractions and normalize these things, okay? You also can do the same thing with secant areas and amplitudes. You can define your A naught and just substitute secant area for composite amplitude thickness, and the formula remains the same. Okay. here is just some quantitative comparison of inversions. You can see the leaded wave inversion versus the adjacent geophysical. I think you can see a bit more sharpness here, and that is, I think you can even visually see the bit better performance. Well, I mean, what can I say about Hampson-Russell there? I mean, they actually think there's a big Mongo thick sand sitting here, but it's just because they had the prior model and they couldn't like pull their solution, you know, that far away from it. And you even look at some more details of this, and it's causes even more sort of other sort of internal pathologies. Well, here is a couple of different plots. I think the things that you really want to look for is how well your net sand thickness matches what your prediction should be. Your prediction matches the actual. The actual is going to be the yellow line. Sometimes we actually add noise to the data in a couple of these plots. If you take a look at the normalized amplitudes, that's also the tuning curve. And you can go and see how much of a sort of overshoot that you end up getting in this case in terms of the expected amplitude. You can see that things aren't going too bad, but then you get all types of problems with local minima around where that particular shale plug is. And you see you're going back and forth, and sometimes it's in one local minima, and other times it's in another. And if you look at the details of the inversion, it's pretty clear what the local minima are that it's getting stuck in. Okay, if you go and take a look at secant area, you have the problem I talked about before, which is this 40%. You end up having a particular overshoot. I do want to say this is on quadrature data, not run sum. So we've just shifted the phase by 90 degrees, and I have not put on a 6 dB per octave high cut. Okay, and let me go and just sort of, I want to say one thing about this is that, you know, pay attention to the fact this is 60% overshoot, okay, which many times is the size of the anomaly we're trying to see. And that this has more high frequency, and many people will go and say, I like this, because why am I going to go and put a 6 dB per octave high cut on my data? That destroys high frequencies. You're going to see you should do it, because all you're doing is artificially adding high frequencies here that cause you to get poor performance in terms of estimating what you need to estimate, okay? Now if we go to the secant area on run sum, we see we've gone down from a 60% overshoot to a 30% overshoot, okay? So there has been a factor of 2 reduction in the tuning effect, which obviously can help. And also we went from 100% overestimate for the thin sands down to only a 30% estimate, and didn't really improve things much on the high end. Let's take a look at composite amplitude thickness. That sort of ends up being sort of intermediate. We have about a 50% overshoot. You have some problems if you don't identify that shale plug, because it actually thinks there's more rather than less where you put in the shale plug, and that goes in the wrong direction. You get 100% overshoot, not the 60% overshoot of secant amplitudes on run sum there. One thing to do note, and this is actually a key to why I think Exxon really likes using it, is you don't have this particular mistake when you get the thick sands. You can correct secant area. If you know you have a thick sand, you know it's 40% under, correct it by that. But I think the key here comes about that I think Exxon's portfolio tended to be very rich in thick stuff. And so they like this because it ends up being, you know, good where you end up having thick stuff. And I think that if you take a look at why, with especially Shell in the Gulf of Mexico, like secant area, is that they end up having multiple interfering sands with finding upward sequences. And when you start having multiple interfering sands, and you start trying to pick top and bases, you start chasing your tail fairly quickly. And I think it had more to do with the particular portfolios of the two companies in terms of what their choices were and the type of amplitudes that they preferred. If you go and take a look at adjacent geophysical, I mean, things are starting to look pretty good here, sports fans. I mean, other than this little underestimate problem here, you know, you're doing fairly well in tracking the net sand. The overshoot is down to 10%, okay? So it's almost in terms of tuning. And so it's really gone and clamped the tuning effect to a point that I don't think it's really significant anymore. And so, that's where, where people sort of have gone and asked me, Mike, why don't you go and worry about tuning corrections on inverted data? It's because of benchmarks such as this. And we really look at the sparse spike inversion as something that goes and reduces that.
So this is using the JSON inversion data set, and is it using the secant area?
Yeah, it uses secant area off of the JSON band limited volume, yes.
There's a few other inversion products now, like Oligard, which you mentioned on the section 2. Did they actually benchmark that when they come out?
I mean, Oligard is probably, I think, sort of close to equivalent in quality, and the generation of the software is fairly similar. We can go and get that and benchmark it. I mean, the thing is, we had, 2 acceptable solutions sitting in-house with good performance, and we, I think that Oligard is something that we seriously thought of getting at the time, but it probably may well have acceptable performance, but we have not directly benchmarked that product. It's a fairly simple thing to give them the wedge model and say inverted.
Yeah, I guess I asked, other operators use a different.
Yeah, if you get in that particular case, I mean, I think that, Guy and Long could easily check into and apply this benchmark to it. So we just haven't had cause to do it. So. This is the let it wave inversion. You see, it's bang on as the earlier one, and it pretty much has no tuning overshoot. So.
It seems to have.
Slight difference.
Yeah, here, go ahead.
The Exxon method, what we call compensating has less scatter when there's a lot of noise in the page.
Okay. Yeah. Yep. No, that's good observation. Okay, doke. And you can probably see, because the tuning overshoot and the matching, we're very comfortable with this. And
Okay.
okay, what's important? Dave talked about intensive and insensitive to phase metrics. Really be careful of RMS amplitudes is really the thing that they're maybe can help. They can maybe quickly focus you on areas, but beyond that, it ends up being some real significant problems. We risk fluid on amplitudes greater than tuning, or off of the sparse spike inversions. Composite amplitude thickness or secant area are proportional to net sand or the amount of economic value in the end. These are soft sands. Sparse spike inversion really does improve the pay estimates and reduces the tuning. JSON is good, let it wave is better. Be careful of composite amplitude thickness when you start getting complicated models, because if you don't really catch every little, internal shale in these things, it can actually grossly overestimate the amount of pay that you have. We do recommend secant amplitude on run sum data. We have this implemented through the workbench in the landmark framework, so we really do recommend that this is an approach that you should utilize. And also, when they talk about this JSON low frequency merge, and some of our partners start saying we want to spend 4 months doing it, I've never, all of our benchmarks and the like indicate that it's wasted effort.
What about porosity? If you want to extract porosities from
That's is one thing that I haven't gone into here. There's a real nice application I can show you on sake, and also on a Mexican field in the Burgos Basin product, where we ended up going and were able to extract porosities. And in fact, what we ended up doing in those cases was to have a probability of a low versus high porosity facies, have hump plots associated with low versus high porosity, and then risk things in terms of porosity, since fluid really didn't make a difference in those cases. So there's a very analogous workflow if you're dealing with a tighter rock or the carbonate type rocks, where the Gaussian substitution effects of fluids aren't significant because of the higher betas of the rocks. So there's a very direct, and also if you go into the phase 2 stuff that we'll be talking about in lecture 12, that explicitly will come up with porosity estimates. You'll see the porosity be estimated and the standard deviation go down on it, so that that can be directly come out of the model-based inversions too. So.
Hard sands, overpressured sands, are they going to be, are we just picking the area on the inversion side, or are there any special considerations that we need to take into account, particularly
Okay, let me go. They're two different issues. Hard sands, many times you have the issue that I talked about, that where you have the pay, you can't see it, okay?
Yeah.
In those cases, you're going to want to form those rotated stacks you were talking to me about and do your pay estimate off of the rotated stack, okay? That ends up showing you what the sand is, okay? Also, multiple stack model-based inversion also addresses that same issue with a hard sand, and we'll use both stacks in order to come up with its volumetric estimate. In terms of overpressure, that you better go and sort of realize that in terms of your modeling, and you'll have to take a careful look at things like seismic velocities. I think we all know that pressure prediction relies on that, and that you really do have to ask about both your seismic velocities, or in the absence of that, your basin modeling, and using the basin modeling prediction. Because one thing that you can't ask Alan Yu for is what the effective stress is, and there are fairly solid ways to relate effective stress to what the properties are. In fact, Glenn Bowers has an expression which I think is very reliable, and in fact is bang on what I've seen derived in other companies in proprietary settings. So, or other proprietary derivations of the same. It says the same functional form, the same coefficients. And in fact, that is also a major thing that needs to be put in. Is the major thing that needs to be put in for 4D. In fact, so it's putting explicitly those functional forms. Does that answer your question, or?
Yeah, the first one.
Okay.
First response.